Hey, hello there. Today I'm looking at the question 502 IPO. So the question is really long. There is actually a TLDR in the question, so just read this first. To sum up, we want to pick a list of at most K distinct projects from the given projects, trying to maximize the capital gain, final capital, and we want to output that maximize the capital. So what are the projects? The projects, for each project I, there are two elements, which are the pure profit, PI. So it's not revenue, we don't have to deduct any kind of cost. It's pure profit that will be added to the capital. And the minimum capital CI, that's needed to start the corresponding projects. That's not actually subtracted in the end. It's actually just a threshold. Once we are big enough, we can get the contract, and since the PI is the profit, so it's the cost is already deducted from there. That's pretty much these two things describing our projects. Initially, we have a capital that's W. When we finish our project, the obtained profit will be added to the capital, so that we can potentially grow larger and be able to get some new contract and lock in that potential additional profit into the capital and grow larger to get larger contract. So that's pretty much how this question is laid out. Looking at the example, we have K equal to 2, meaning that we can do at most 2 projects, maybe before some deadline, the IPO timeline. And our initial capital is actually 0. The profits are 1, 2, 3 for the 3 different projects, and the capital requirements, it's not the cost, it's the capital requirement to obtain that profit. The associated profit is 0, 1, 1. So we don't have any initial capital. That's so the first project is the only one that we can do and to obtain its profit. So once we finish that, we add 1 to W. So now our total capital is now 1. Looking at the remaining 2 projects, their requirement capital is 1, so we could do either one of those. Obviously, we will go for the one that's yielding the larger profits. So we go about do the third projects. After we finish that, now our total becomes 4, and we have done 2 projects. So the maximized capital is going to be 4. So that's this example. Pretty cool that with no capital, we could do something and get profits, making money out of thin air. Anyway, so just based on this example, you can see that the choice here among the available projects that we can do, since that these are requirements, it's just a threshold to test the doable or not. It's not actual any kind of cost. For all the projects at any given time, when we need to make a choice, among all the projects that we can do, we will definitely do the one that yields the highest profit. Because once we do that, our capital can grow higher, so maybe unlocking some other projects that will potentially yield more profits. So basically, what we want to do is to each time when we finish a project or yet to start a project, we look at all the projects that we can do. Now our current capital is larger than the required capital. We pick the one with the largest profit and add that to the now total capital. Once we do this K times, we're done. So it's going to be a for loop or a loop that's running K times, and each time we will look at all the options that's below our capital threshold and pick the one that's with the highest profit. So definitely we can use a priority queue to hold the set of projects that we can actually do, and it's going to be a maximum priority queue, so that the top elements is going to be the doable project with the highest profit. But once we raise after we finish a project, our capital grows, we want to grow the set of projects we can do on the priority queue. we can do so by pulling the next cheapest, capital least capital demanding projects that was originally undoable. Just put that into our consideration set. So for that reason, we could have another priority queue to hold the undoable projects, using a mean priority queue based on their capital, so that once we finish our project, we try to look at the not doable project from the prior time, and just pull the least expensive one, least capital demanding one, and put that into, if we can do it now, we move that basically into our consideration set. Once we do that, once we updated the consideration set, we try to pick the next one that's yielding the most profit. So 2 priority queue. And that's pretty much how to solve this, and it's pretty intuitive and straightforward. The reason why greedy works is that this is not cost. If this is cost, we're going to take the difference. If this is cost and revenue, the problem will actually become much more interesting. So here it's really simplified. And greedy just works because among all the projects that our capital allows us to do, there's no reason to go for the projects that years 2 when we can do a projects year 3, because this value here is not subtracted by from the W. All we do is to find the highest P and to put that onto W. So that's why greedy works. So with that out of the way, let's start code this. All right. So the consideration set priority queue is easy because that's just going to be the priority queue of the profits. So it's the easier one. The other one that has to have a tuple on the priority queue, it's going to be the capital and the profits, because when we sort it, we sort based on the on the capital in the increasing order. So it's a mean priority queue. Once we pull it, we want to grab the second element, which is going to be the profit, and put that profit onto the second priority queue. So there are going to be 2 priority queue. One is just going to be container is just going to be integers. The other one is going to be a pair. So let's define a type. Let's call this and the default priority queue in C++ is maximum, so that works fine for the profit priority queue. But for the least capital demanding projects priority queue, we need a mean priority queue. So we need to provide a comparator. So it's going to be just a public here. We're going to have a operator, and it's going to take 2 pairs, 2 tuples. We want to have this in the we want the first to be larger than the second, so this comparator be used by a maximum priority queue will become the mean priority queue. It's tricky. Yeah, so that's the comparator. So now we basically just gonna initialize this priority queue first. So we grab the number of projects, and we're gonna initialize this in a vector of tuples. So this is basically just creating the underlying container for the project's priority queue, and we're gonna move this onto there, and just do one make heapify operation. So it's gonna be linear time. This creation is also linear. Queue. The elements on there is gonna be this pair tuple. And the underhood container is a vector of II, and the comparator is this self-defined one. Let's just call this project's priority queue. And to construct this, we do this. We pass in actual instance for the comparator. Because I couldn't pass in a class here. Class is not the first class object. And then just move this vector of projects onto here. So you would actually call a make heap, I think, to make this thing heap ordered. So that's this project priority queue. We're gonna pull the least capital demanding project from this priority queue and push out onto the consideration set. So that's this priority queue. The other priority queue we will use is just the pure profits maximum priority queue. That's all the projects that we can consider in looking at the maximum profits. Let's just call this feasible. Yeah, so that's initially empty because in the case that we have zero money, if there is no projects with zero capital requirement, there's nothing going to be feasible, so it's totally empty in the beginning. So the looping condition is that while we haven't done K projects yet, we're going to do this. What we're going to do is to try to pull the projects that we can do into our consideration set. So while this is not empty, and that the cheapest, the least capital demanding projects, its requirement is less than the current capital that we have, the W. What we're going to do is to pop this and push this onto the feasible. Nope. Oh, sorry, feasible. I should copy this. Gonna put the profit onto this priority queue and pop it off. So after this while loop, we can just find the most rewarding projects from feasible and add that profit onto the capital. So what? Why it's did I delete anything? I just no idea why that happened. Yeah, so just continue. So we want to do is to increment the W by the largest profit we can do now. So that's from feasible. And then pop this out because we couldn't do duplicates. Duplicated projects. So that's that. I think there is just one thing that we need to handle. That's if the feasible become empty. That means we haven't finished the K projects yet, but we have no projects we can do. Then the W is the one that we should return. There's no way we can increment W anymore, so that's why we return it here. Otherwise, we would try to pop off something from nothing. There's no way we're gonna be doing that, so that would cause problem. So that's pretty much the code, I think. Let's just do some quick checking. Yeah, looks okay. Let's see. Nope. Misspelled. This is first. Anything else? Nope. Why would I have that? Okay, this time? Yeah, it seems so. Let's try to submit this. That's working. Okay. So let's look at the runtime. So here, the construction of this is order of n, because we push n elements onto this vector. So that's order of n. And here, the heapify would take order of n. I'm not sure if it's moving or copy. I'm not a C++ expert, so but anyway, the time required for this to become heap ordering should be linear time with respect to the number of elements. So that's order of n there. Here, it might be tempting to say that it's a k multiplied by something, but actually no, because this while loop will be terminated early, and the most number of time that this while loop multiply, in its entirety of this k repetition of this while loop, the total is just going to be popping everything out, so it's going to be n log n. So this while loop is going to be n log n in total. So that's this, because in the worst case we pop up every project from this priority queue onto the feasible, and the feasible, when we do the pop, it's gonna potentially we push this, so it's 2 multiplied by n log n, because we push this and pop this. If feasible grow as large as the total size, that's that. And here, the pop here only runs at most k times. So yeah, so the total runtime will be sorry. So the total runtime would be 2n plus k plus 2n log n. Yeah. So dropping a constant, this n linear term is overshadowed by the n log n. So yeah, it's if k is relatively smaller compared to n, this becomes a n log n. Yeah, all right. So that's the time complexity analysis. The space is obviously linear. This one is linear. This two is potentially linear, maximum in the worst case. So yeah, so that's this problem. 2 priority queue, 1 to continuously grabbing the least capital demanding projects, so that once we do some projects, this can potentially be something we can consider. So we grab the least capital demanding one at a time until we until the thing that's the least demanding, it's something that we couldn't do. So we use that for that reason. The second is for the current doable projects. We want to grab the most profit awarding projects. So that's the use for another priority queue. Yeah, so that's this. There is just something that we could do this a little bit simple, so that for the projects we just sort that entirely. here we're just trying to avoid the full sorting. The other way is just using one priority queue, the feasible, and just do a full sorting of this projects in the very first run. Just creating this and sort this vector, you would do too. We just have an iterator, and so the next time you will come up with the least demanding, because you traverse with the iterator, it's gonna work too. Here I'm trying to avoid doing extra work, but based on the runtime, it's actually slower compared to sorting, I think. But it doesn't really change that the fact it's going to be n log n, because if you sort, it's n log n there. So overall, the runtime should be similar. Yeah, I should say the time complexity should be the same territory. There's no theoretically better. It's just based on the data you have. So you could potentially behave differently. Yeah, so that's this question today for use of two priority queues. Yeah.